Alright, so we just did the example with the power. And so how is work related to energy? So work is actually the change in energy, and energy is considered the ability to do work. Okay, so the way we write that is that the work in joules is equal to the change in energy also in joules. So anytime you're changing energy levels, you're doing work. Okay, so just to remind ourselves, the change in energy is going to be anytime you have a delta right here, it's the final quantity minus the initial quantity. So that's just another way of writing the work. The work is E final minus E initial, or delta E. Okay, so that's when we're changing energy levels. All right, let's go back to the PowerPoint, and alright, so yeah, work is the process of changing energy levels, as it says there. And we're going to look at the relationship between work and energy associated with position. So that's remember I mentioned before that there are basically two types of energy that we're going to talk about in this chapter. Potential energy, which is the energy of position, and kinetic energy, which is the energy of motion. Alright, so let's look at potential energy. Now, as I said before, there are many types of potential energy, and one type is the type that we'll primarily talk about in this chapter. So here, let me scroll down a little bit. So as I said before, there's many types of potential energy, and here's the thing about energy, or potential energy and kinetic energy. This is the only time that you use two letters. Normally it's one letter, like M is equal to mass or E is equal to energy. So for potential energy, you use two letters, PE, and like I said, there's many forms of it. Primarily what we're going to use in this chapter is what's called gravitational potential energy. And so that is the energy that something has according to its position, its height. Okay, so its height above some reference point. And usually the reference point is a height of 0. So like the height right at the floor here, the height would be equal to 0, and h is the height of this mass m above the floor. So the way this works is it's really the weight of the object, which is the mass of the object times gravity, and then what potential energy is, it's times the height as well. Alright, so let's go over the units of this. Potential energy is measured in joules, just like energy always is. Okay, joules. The mass here is in kilograms. Little g is what it always is on the surface of the planet Earth, 9.8 meters per second squared. And h, as you might guess, is in meters. So if you multiplied all that together, you'd have kilograms meters squared times seconds divided by seconds squared, and that turns out to be what a joule is. Okay, so let's go back to. I guess we could do a quick. Let's do a quick potential energy. So let's say let's go back and look at the equation here. One of the things to note is the mass times gravity is the weight. So if you're already given the weight of the object, then all you have to do is multiply by the height. So let's actually give some numbers to this. Let's say the mass is 5 kilograms. Sounds like 5, and the height is let's say 10 meters. So you raised an object 10 meters above the ground, so this is the height above the ground, or some reference point, where the reference point is always h is equal to 0. Like the initial height is 0. All right, and we raised it 10 meters. Okay, so it's really simple. It's just going to be 5 times 9.8. 5 times 9.8 times the height, which is 10. Okay, so so the potential energy of this object, whatever it happens to be, is 5 kilograms times 9.8 meters per second squared times, what was the height again? Oh yeah, 10 meters. Alright, and so I'll do that in my calculator real quick. So 5 times 9.8 times 10, I get 490. So 490 is the potential energy. 490. Alright, so that's, and of course the units are joules. Alright, so that's the potential energy of this object right here that is 10 meters above the floor. And so another way of looking at this, remember, work is the change in energy levels. So if the object, this 5 kilogram object, was originally on the floor and we lifted it, we've done how much work we've done. Since at the floor the height is 0, the potential energy there is 0. Okay, so that's something really important to realize. So the potential energy right at the bottom here is 0, and then you lift it through a height of 10 meters. What you've done is you've done 490 joules of work, right? Because the work, in this case, let's say you don't change the speed or anything, it's just the change in potential energy. Change in potential energy. I guess I should, let me point one other thing out here, is that the total energy, and the PowerPoints are probably about to tell us this, the total energy is the sum of what's called the kinetic energy, which we'll get to, plus the potential energy. And so the change in energy is going to be the change in the kinetic energy. So if we had a change in the total energy, there would be a change in kinetic energy and or a change in potential energy. So if one of these two things, if the potential energy changes, then the energy changes. If the kinetic energy changes, the energy changes. If both of them change, the energy changes as well. Alright, very nice. So here, let's go back to this. So we just did a little example, and what we're ultimately getting to is what's called the conservation of energy, where you conserve both the potential energy and the kinetic energy, and we'll do some problems like that. So here's the equation for kinetic energy. So kinetic energy is 1/2 the mass of an object in kilograms times the velocity, where the velocity is going to be squared. So we square, the velocity is of course going to be measured in meters per second. The kinetic energy, just like any form of energy, is measured in joules. So here we are, here's the kinetic energy, which is 1/2 the mass of an object times its velocity squared. And again, let's just go over the units. I know I just did this, but kinetic energy is in joules, the mass is in kilograms, and the velocity is in meters per second. All right, so and remember, you're squaring the numerical value of velocity. Let's do a problem. Let's see, how much time do I have? Here's the problem. Let's say we have a car and its weight. So remember, this is the script W for weight, which of course is mass times gravity. Let's say the weight is measured to be, I don't know, how about 12,400 newtons. So that's the weight. But of course, looking back at this, we don't need the weight, we need the mass. But of course, we have this equation: the mass times gravity is the weight. So we could immediately solve for m by dividing both sides by g, and so 12,400 newtons divided by little g, which of course is 9.8 meters per second. Remember, meters per second squared. Remember, if you know the mass, you know the weight, right? If you know the mass, you know the weight. Conversely, if you know the weight, you know the mass. Okay, so you just do a simple calculation, and we'll calculate. All right, so here's the calculation. The mass turns out to be 1,265.3 roughly kilograms, right? So now what we can do is to figure out the kinetic energy. Oh, and I guess I gotta. So this is a car that has this for the weight. Let's say it's moving with a velocity. Usually it's going to be given to us in kilometers per hour. I'm not going to do that right now. We'll just to simplify things. Let's say it's moving at 7.4 meters per second. All right, so 7.4 meters per second is the velocity. We're going to put that into the kinetic energy equation right here, and so let me set that up. All right, so I've just put the numbers in right down here. Remember, you're only squaring the velocity, the 7.4 meters per second, and so the kinetic energy is 644, roughly 0.1. It's like 0.08 is on my calculator, and of course that's in joules. So that's how fast, that's how much kinetic energy the car has traveling at 7.4 meters per second and weighing 12,400 newtons. Okay, so and also just to let's say that the car was moving on a flat surface. Okay, so here's our car, and it's just moving horizontally. Okay, I can't draw very well, but if it's just moving horizontally and we want to know how much work it would take to stop the car, right? So let's say it's already moving with a velocity of 7.4 meters per second, 7.4 meters per second in this direction. The amount of work to stop it, it's kind of interesting. You would say, well, it's going to be the work, it would be the kinetic energy final. Since we're only dealing with kinetic energy here, right, it's not changing height, it's going to be KE final. But if we're bringing it to a stop, then the final KE, the final velocity will be 0, so the final kinetic energy will be 0. So that's the final, and minus the initial. And so what's the initial? Well, it's this. It's the kinetic energy it has as it's moving down the road, and a flat road. So it's minus 34,644.1 roughly joules. So it's negative this original amount that what the negative indicates is we have to remove energy from the system. We have to remove 34,644.1 joules, and that will bring the car to a stop. If the car was stopped already and we wanted to bring it to, a speed of the same car, the same weight, to a speed of 7.4 meters per second, then, of course, to bring it up to that speed, it would be positive. You'd be doing positive 34,644.1 joules, right? Because the final kinetic energy would be exactly equal to that, and it would start out with 0 because it was at rest.